Hello, let's begin one more lecture session on multivariate calculus integration. We have been speaking of triple integrals. We have seen that the triple integral of the function f of xyz over a region U is denoted as triple integral f of xyz dx dy dz over U and is defined as the limit of the sum as limit maximum of delta xi tends to 0, maximum of delta yj tends to 0, and maximum of delta zk tends to 0, summation of f of uy vj wk, delta xi, delta yj, delta zk, where I goes from 1 to m, j goes from 1 to n, and k varies from 1 to l. And here, this EYVJWK is a point in the elementary rectangular box with dimensions delta xi, delta yj, and delta zk in the x, y, z directions respectively. Now, today we will see how to evaluate such triple integrals. And this is essentially by repeated single integrals. This is exactly same as we have seen in case of double integrals. The only difference being that now triple integrals will be evaluated as three repeated single integrals. Let us see first the simplest case, a rectangular parallelepiped. So our region U is a rectangular parallelepiped with the dimensions AB cross CD cross PQ. Suppose it looks like this, where it extends from A to B in the x direction, C to D in the y direction, and P to Q in the z direction. So now, how to evaluate a triple integral? This is again given by Fubini's theorem that the triple integral f of xyz dx dy dz over the region U will be given by this formula, which says that first we are evaluating the function f of xyz with respect to z from p to q. Now, once this integral will be evaluated, the result will be a function of xy, which will be next integrated with respect to y from c to d. The result of this second integral will be a function of x, and this is finally integrated with respect to x from a to b. However, note that this is not the only possible way. Actually, there exist 6 possible orders to evaluate the integral. So, for example, first maybe we have evaluated this integral with respect to z, but next one, instead of y, we could have integrated with respect to x and then with y. Or otherwise, we may first start integrating with respect to x or y also. So in totality, there are 6 possible orders to evaluate this integral. Let's now look into a problem. Evaluate the integral 8xyz dx dy dz over the region U 2, 3 cross 1, 2 cross 0, 1. So let's see how to do it. So the triple integral 8xyz dx dy dz over U can be written like this. What we are doing here, that we are integrating this function 8xyz first with respect to z, and the limits of z as given here are from 0 to 1. Next, observe that we are integrating now with respect to x, and the limits of x as given in the region has been taken as 2 to 3. And lastly, we will integrate with respect to y from 1 to 2. And note that this is not again the only possible way. It is very much possible to evaluate this integral in some other order. Okay, but now as written over here, let's proceed. So as we are first integrating with respect to z, this gives us 4xyz square and the limits are from 0 to 1. Once we put the limits, we will get 4xy now as the integrand. We integrate with respect to x, so it gives us 2x square y we have to put the limits from 2 to 3. This will again give us 10y dy, which is integrated now from 1 to 2. And the final answer will be 15. Okay, now let's move on for evaluation of triple integrals in arbitrary region. Now, as we talk about a general three-dimensional region, it can be actually classified into three types: type 1, type 2 and type 3. Let us see one by one what are these. So the type 1 region is actually classified like this, where the region U is bounded below by the surface z1xy and at the top by the surface z2xy. So the region is actually such that any straight line parallel to the z-axis intersects the boundary of the region U in no more than 2 points. And see that dxy is nothing but the projection of the region onto the xy plane. So now this region U may be represented as the set of points xyz such that xy belongs to this region dxy and z varies from the lower surface z1xy to the upper surface z2xy, where of course we assume that z1xy and z2xy are continuous functions of x and y. And now how do we evaluate this integral? See that now our formula tells like this, that for any continuous function f of xyz in the region U, we can write the triple integral f of xyz dx dy dz over U in this form, where we have an inner integral which is first integrated with respect to z from the lower surface z1xy to the upper surface z2xy, and the result of this integration is now integrated for the region D in the xy plane. So essentially what is happening, that the calculation of the triple integral has been reduced to calculating a double integral where the integrand is a one-dimensional integral. Okay, and next how do we proceed? Of course, we have to see how to evaluate this double integral, but that is something known to us. And we know that when we evaluate a double integral in a general region, it can be classified either as a type 1 region or as a type 2 region. So first let us suppose that dxy is a type 1 region in the xy plane, and let us suppose that it is bounded by the lines x equal to a, x equal to b, y equal to f1x and y equal to f2x, where f1x, f2x are continuous functions on the interval ab and f1x is less or equal to f2x. Then we can write again the double integral as an iterated integral, and finally what we get is over here that the triple integral f of xyz dx dy dz may be evaluated with this formula as 3 repeated single integrals. So what we are finally doing is we first integrate with respect to z from z1xy to z2xy, the lower surface to the upper surface. Next, with respect to y, from the lower curve f1x to the upper curve f2x, and finally with respect to x from a to b. Now, if our dxy is of type 2 region, then let us see the formula. So, if it is bounded now by the lines y equal to c, y equal to d, and x equal to phi 1y and x equal to phi 2y, where phi 1y and phi 2y are again continuous functions on the interval cd, such that phi 1y is less or equal to phi 2y, then the formula for the triple integral may be written now like this, that once again first we integrate with respect to z from z1xy to z2xy, and now next with respect to x from the left curve phi 1y to the right curve phi 2y, and finally with respect to y from c to d. So we have seen how to evaluate triple integrals for type 1 region. Next we will see the type 2 and the type 3 regions one by one. Now, what is a type 2 region? Let us see in this figure. So it is essentially like this, where we assume that x varies from this surface u1yz to the surface u2yz, and the projection of this region lies on the yz plane, written as d of yz. So therefore now the region u may be represented as the set of points x of yz, where yz belongs to D and x lies between u1yz and u2yz. And now let us see the formula for the triple integral. This is now like this, that first we integrate with respect to x from u1yz to u2yz, and then we have to evaluate the double integral in the yz plane. And that can be done in our known way, how to evaluate the double integral. Let's now see the type 3 region. So the type 3 region, we can guess that it is the region whose projection lies in the xz plane. So it is like this. So this is a type 3 region bounded between y equal to u1 xz and y equal to u2 xz, and the projection lies on the xz plane. So the region U may be now represented by the set of points x, y, z, where xz belongs to D and y lies between u1xz to u2xz. The formula for the triple integral is now as follows. So we will first integrate the function with respect to y from u1xz to u2xz, and then we would evaluate the double integral on the xz plane. And final formula will be, of course, repeated 3 single integrals when we will evaluate this double integral as repeated single integrals. So we have seen essentially all the formulae how to evaluate triple integrals in type 1, type 2 and type 3 regions. The problems to see how to evaluate such triple integrals will be taken up in the next lecture session. So thank you and goodbye till then.